Chapter 2. Storage. We pop A2 and we append C2. Here is the new constraint. Memory and disk access incur different costs in both time and money. Memory is significantly more expensive and much faster to access than disk. And on disk, sequential access is substantially cheaper than random access. Furthermore, even absent a power failure 20 drained which is still excluded by A7 at this stage, memory remains volatile and can lose state due to software errors. Notice that three separate asymmetries arrive together there. Memory versus disk in money, memory versus disk in speed, and sequential versus random access on the disk itself. Those are independent facts, and different structures exploit different ones. Nothing about concurrency changes in this chapter. What changes is that a data structure is no longer a neutral container. A data structure is now a bet about which accesses will be cheap. Look at the cost hierarchy on screen and read it top to bottom. CPU, registers and cache, fastest, costliest per byte, and tiny. Main memory, fast, expensive, and volatile. Sequential disk access, cheap and durable. Random disk access, still cheap per byte, but expensive per access. And that last distinction is the one that shapes everything in this chapter. So the new design question is this: how do we arrange and place data so that the operations an application actually performs land on the cheap side of that hierarchy? Three families of answer follow immediately. Turn writes into appends, so they're always sequential. Reduce the number of seeks per query by putting more keys in each unit you fetch, or keep only an index resident in memory and leave the bulk on disk. Each of the structures we are about to see is one of those bets. Let's start with the simplest. A hash index is an in-memory hash map whose keys are the unique identifiers of records and whose values are the corresponding byte offsets of those records on disk. The underlying on-disk structure is an append-only log. Every write is appended sequentially to a segment file. Follow what that buys and what it costs. A point lookup is one hash computation and one seek. The map tells you exactly where to land. Every write is sequential. Because you never seek to write, you only ever append to the end of the current segment. An update simply appends a new record, and the superseded one is dead weight until it's cleaned up later. This design supports very fast point lookups and high write throughput, but it does not support efficient range queries because there's no ordering in the log at all. So answering a range query would mean scanning everything. And the in-memory hash map must be small enough to fit in main memory, which places a hard ceiling on the number of distinct keys the structure can efficiently support. Two ideas from this structure survive into everything later in the chapter: segment files and appending instead of updating in place. Hold on to both. Fastest possible writes, then at the cost of ordering. The next two structures buy ordering back, each at a different price. A B tree is a balanced search tree with a much higher fan-out and a correspondingly lower height than a balanced binary search tree. It achieves this by storing multiple sorted keys per node. Nodes are stored as fixed size, contiguous blocks on disk, which allows several keys to be retrieved in a single disk seek. And that is precisely what makes the B tree well suited as an on-disk structure. B trees support both point queries and range queries efficiently. High fan-out is the entire trick. A binary tree costs you roughly log base 2 seeks. A B tree costs you roughly log base fan-out seeks. And because the node is sized to the disk's unit of transfer, one seek returns many keys at once. This structure is shaped by the medium, not by theory. The B plus tree is an optimization of the B tree, and it's the structure most commonly used in relational database engines. Here's the refinement. Internal nodes store only separator keys, used purely for routing, while all key value pairs are stored in the leaf nodes. Because the internal nodes no longer carry values, more keys fit in each block, which increases fan-out and reduces tree height relative to a plain B tree. Leaf nodes additionally maintain sorted key value pairs, and this is the part to watch on the diagram. They are linked together so that a sequential range scan can walk sideways from leaf to leaf without retraversing the tree. So the B plus tree makes both point queries and range queries efficient. The cost it accepts is that updates happen in place, which means random writes. That cost is exactly what the next structure refuses to pay. The LSM tree, or log structured merge tree, is a disk resident structure used extensively in modern NoSQL databases. It's built from several cooperating components that are periodically merged and compacted in the background. Let me take them one at a time, and I'd encourage you to follow the right path and the read path separately on the architecture diagram because they're genuinely different journeys. The mem table is an in-memory sorted structure, typically a balanced binary search tree or a skip list that buffers incoming writes before they are flushed to disk. Reads consulted directly for any key not yet flushed. The SS table, or sorted string table, is the on-disk structure, a collection of segment files, each storing a sorted run of key value pairs together with a sparse index for efficient lookup. The write-ahead log, yes, the same mechanism from Chapter 1, in its second appearance, is a disk-resident append-only log that records every modification applied to the memtable before that modification is considered durable. It provides the basis for crash and transaction recovery. Data buffered in memory is periodically flushed or checkpointed to disk, after which the corresponding write-ahead log entries can be discarded. And the Bloom filter is a probabilistic, space-efficient structure that determines, with no false negatives, though with a tunable rate of false positives, whether a key is definitely absent from a given SS table. That lets the read path avoid unnecessary disk reads against segment files that cannot possibly contain the key. It's the one place in this chapter where being approximately right is good enough, and the asymmetry is what makes it safe. A maybe present costs you a read you might not have needed, while it definitely absent is never wrong. Now, the defining characteristic of the LSM tree approach, and the reason all of those pieces are shaped the way they are. Segment files are written once, sequentially, and are thereafter treated as immutable. Since encoded key, value entries also vary in size, true in place updates are impractical anyway. So updates are instead appended as new entries. Deletions are recorded as tombstones. A deletion is itself a write, and superseded or tombstone entries are physically discarded during background compaction, which merges overlapping segments and keeps both the read path and the space overhead bounded. Nothing is ever erased in place. The cost of that discipline is deferred to compaction, where it is paid sequentially on the cheap side of the hierarchy. So let's put the two ordered structures side by side, because this is a decision you will actually make. On write throughput, the LSM tree wins sequential appends versus the B plus tree's random in place page writes. On the predictability of point read latency, the B plus tree wins one path of bounded depth versus a read that may have to touch several segments. On range scans, the B plus tree walks its linked leaves, while the LSM tree merges across sorted runs, and both carry background overhead of different kinds, compaction and dead entries on one side, page splits and fragmentation on the other. So ask what dominates the workload. High volume appends with few updates, logging, time series ingestion, event streams favor the LSM tree, read heavy, range query heavy workloads over mutable rows, which is the classic OLTP shape, favor the B plus tree. And if you only ever do point lookups, and the key set genuinely fits in RAM, the hash index is sufficient. There is no structure that is simultaneously write optimal, read optimal, and overhead free. C2's price list forbids it. And note the scope discipline here. Both of these structures are still single machine structures. A 3 has not been popped. No partitioning question exists yet. Let's move up a level from data structures to data models. Different data models are optimized for different data properties. The size of the objects, the relationships between those objects, one-to-one, one-to-many, many-to-one, and many-to-many, and how rigidly a schema is enforced. An in-memory DBMS stores data exclusively in RAM and serves reads and writes with very low latency. But the data it holds is not durable by default, and its total capacity is bounded by the cost and the volatility of RAM. Then there are the disk-based systems, and the first family is the relational one. Relational databases store structured data that conforms to a fixed schema, provide asset guarantees natively, and are queried using SQL. Data is organized into tables of tuples, each with a primary key and additional attributes, typically stored in a row-oriented layout. Normalization eliminates data redundancy by decomposing data about different entities into separate tables, linked by foreign keys, and joins are what reassemble it when you query. There's a well-known drawback, and it's worth naming precisely: the impedance mismatch between the relational model and the in-memory object structures used by application code. An object in your program is one nested thing. The same information in the database is rows across several tables. Bridging those two representations requires an explicit mapping layer, either an object relational mapper or hand-written queries based on relational algebra. NoSQL databases are a family of more flexible, historically non-ACID compliant data models optimized for semi-structured or unstructured data, horizontal scalability, high availability, and low latency, generally at the cost of strong consistency guarantees. These simpler data models also avoid the impedance mismatch problem and typically avoid the need for expensive join operations. And notice something about that trade. Horizontal scalability and high availability are benefits that only start to pay once A3 and A4 are gone. We're naming them here, but we can't yet motivate them. The common categories are these. A key value store holds data as key value pairs, where the key is a unique identifier and the value may be an object of arbitrary complexity. It's well suited to session-oriented workloads, where access is always by primary key. A document database stores self-describing documents, hierarchical, tree-structured records whose shape may vary from document to document. It suits unstructured data or complex nested structures that are naturally stored and retrieved as a single unit. A columnar database stores data on disk column by column rather than row by row, which makes retrieving a subset of fields, as an analytical aggregation query does, significantly more efficient. It's best suited to read heavy analytical workloads. A wide column database stores semi-structured data with a flexible per-row schema, organizing data into rows grouped by column families. This layout is generally better suited to write heavy workloads than the columnar model. And please note, columnar and wide column describe two distinct storage strategies despite the similarity in name. That confusion is common, and it's worth deliberately avoiding. And a graph database uses a graph structure for storage, where nodes represent entities and edges represent relationships between them, each carrying its own set of attributes. It suits data with a high, irregular degree of interconnection, and queries such as shortest path and reachability, which are awkward to express relationally. Beyond those general purpose models, there are engines built for a single access pattern, optimized hard. A time series database is optimized for storing and querying timestamped data. It's designed for high throughput ingestion, uses compression algorithms tailored to time series data patterns, and is optimized for time range queries and downsampling. A geospatial database is optimized for storing and querying location based data. It commonly implements geohashing, dividing the Earth's surface into a grid and assigning each cell a hash in order to index spatial data efficiently. And notice what that accomplishes. Nearby places end up sharing a hash prefix, which turns what is near me into a prefix or range query on an ordinary index. That's the B plus tree's range locality from early in this chapter, reused on a new problem. A full text search engine is optimized for search over unstructured text. It's built on an inverted index, which maps each term to a sorted list of the documents containing it, so that a multi-term query reduces to a merge of those sorted lists rather than a scan of the documents themselves. A vector database is optimized for semantic search over unstructured data, represented as high-dimensional embedding vectors. It answers similarity queries by locating nearest neighbors under a distance metric, such as cosine or Euclidean distance. To sustain high volumes and high dimensionality, implementations rely on approximate nearest neighbor search, indexing the vectors with structures such as hierarchical, navigable small world graphs, and trading a tunable loss of recall for lower query latency. And a blob store is optimized for storing large, immutable, unstructured objects, photos, video, audio, executable binaries, and other multimedia, typically as chunked files, designed to scale horizontally while remaining highly available and durable. The general lesson about specialized engines: each one is a general engine with an assumption of its own added back. That's only a good trade when the assumption genuinely holds for your workload. Now, for the last mechanism in this chapter, which applies the same reasoning in a different place. Caching applies C2's cost hierarchy across a tier boundary, rather than within a single structure. We'll discuss it in the context of the memory and disk tiers of a single machine. A hot subset of the data is held in memory, which is fast, expensive, and volatile, while the authoritative copy remains on disk, which is slow, cheap, and durable. What distinguishes one caching strategy from another comes down to a single question: where is the write acknowledged, and does it populate the cache at all? Because those two choices fix three things: how far the cached copy will drift from the durable store, which tier a read must consult in order to be correct, and how much data sits exposed on the volatile tier. Write through. A write is applied to cache and disk together and acknowledged only once both have completed. A read is served from the cache when the key is present, and a miss loads from disk and populates the cache before sending a response. Because both tiers are updated in lockstep, neither copy is ever stale with respect to the other. The costs are write latency bounded by the slower tier, and cache space spent on data that may never be read. Write back. A write is acknowledged as soon as the cache is updated, and the disk is written asynchronously, often coalescing repeated writes to the same key into one. Reads must be served to the cache, falling back to disk on a miss, since until a flush completes it is the cache, and not the disk, that holds the current value. This gives the lowest write latency and absorbs bursts. But whatever has not yet been flushed is lost if the cache crashes, and under C2, remember, that includes the loss of memory to software errors, even though node failure and power failure remain excluded by A7. Write around. A write goes directly to disk, bypassing the cache, and any existing entry for that key must be invalidated. The cache is populated later on a read miss. This keeps write heavy, rarely read data from displacing hot entries. The costs are a guaranteed miss on the first read following a write, and a stale read for as long as an invalidation is delayed or missed. And because the fast tier is bounded, every strategy additionally needs a policy for deciding what to discard. Replacement policies infer future usefulness from past behavior, evicting the least recently used entry or the least frequently used entry. A time to live, by contrast, discards an entry after a fixed interval regardless of use. That bounds how long a cached value may disagree with the durable copy, wherever the two can diverge at all, and it does so without requiring the writer to know which entries exist in the first place. Let me summarize Chapter 2. Assumption A2 treated memory and disk as interchangeable, costless, and durable, so Chapter 1's concurrency mechanisms could be layered on top of storage with no regard for where data physically lived. Constraint C2 puts a real cost hierarchy in its place. Memory is fast but expensive, and notwithstanding A7 not yet being relaxed, still volatile to software faults, while disk is durable and cheap but penalizes random access relative to sequential access. Storage design therefore becomes the problem of arranging and placing data so that the operations and application actually performs land on the cheap side of that hierarchy. The chapter's mechanisms address that problem at three levels. The data structures differ in which access they make cheap. Hash indexes turn every write into a sequential append, and answer point lookups from an in-memory map, forfeiting efficient range queries and bounding the key space by RAM. B trees and B plus trees keep both point and range queries efficient, at the cost of more expensive in-place updates. And LSM trees absorb writes in memory and flush them as immutable sorted runs, trading read amplification, mitigated by Bloom filters, for consistently sequential writes. The data models repeat the same tension one level up. Relational systems buy strong invariance and a rigid schema at the cost of the impedance mismatch and more constrained scaling, while the NoSQL family and the specialized databases give up generality in exchange for a layout matched to one axis shape. And caching then applies the same reasoning across the boundary between memory and disk, rather than within a single structure where the choice between write through, write back, and write around fixes how stale the cached copy may become and how much unflushed data sits exposed on volatile memory. The recurring trade-offs are therefore write efficiency versus read efficiency, memory cost versus disk cost, rigidity versus flexibility, and freshness and durability versus latency. In practice, LSM-based engines fit write-heavy, append-like workloads such as logging or time series ingestion. B plus trees fit read-heavy workloads dominated by range queries, the traditional OLTP case. Relational databases fit applications where strong invariance and complex relationships matter more than raw scale. NoSQL variants fit applications where horizontal scale and schema flexibility outweigh the need for strong consistency. The specialized databases are worth their narrower scope only when the access pattern is itself narrow and well-defined. And caching is worth its staleness only when reads concentrate on a small, reusable subset of the data, with write-back reserved for cases where the durability window it opens is acceptable. No single structure, model, or caching strategy is preferable across all of these dimensions simultaneously. Everything we've built so far still lives on one machine. Chapter 1 gave that machine an honest sense of time. Chapter 2 gave it an honest price list. But we're still assuming that everything we own fits inside it. Let's remove that next. and storage stops being a local optimization problem and becomes a distribution problem.